as a topic and the theory of active learning and sort of the beginnings of why in special cases you can have a theory of active learning, a theoretically sound approach to active learning, and also some ideas about why maybe there was a general theory of active learning as well. What I'm going to be talking about in the second part here is indeed a general theory of active learning in more detail, general descriptions of algorithms and descriptions of the number of labels that are sufficient to achieve guarantees on the error rate expressed in terms of complexity measures. I'll say that the theory I'm going to be describing here, referring to the question that was asked, I'm going to be expressing everything in terms of the VC dimension. That's mainly just for simplicity. Many of these results would also generalize to things like covering number. You could express them in terms of things like covering numbers and even localized covering numbers. And that would actually also address many things that aren't covered by bounds expressed in terms of VC dimension. But for simplicity, we'll stick with VC dimension throughout. OK, and I'll mention that this segment, the second part of the tutorial, is covered very thoroughly in a monograph that I wrote a few years back, Theory of Disagreement-Based Active Learning. It is freely downloadable off my website. Or if you want a bound version, I think you can purchase it off the publisher's website. OK, so Rob introduced Hoeffding's inequality and a uniform version of Hoeffding's inequality. For the purpose of stating sort of the tightest results that we can get in disagreement-based active learning, I'm going to need something just slightly tighter than that. So this is what's sometimes called Bernstein's inequality. Basically, it's just like Hoeffding's inequality. So if you have any two classifiers, the difference of their risks is bounded by the difference of their empirical risks plus a term that's looks like the Hoeffding bound, right? The square root of a log 1 over delta over m, except we're now multiplying inside by the fraction of the data on which the two classifiers disagree with each other. And we're just talking about binary classifiers. So this is saying one of them is 0, or sorry, let's say plus minus 1. So one of them is plus, one of them is minus. OK. So that's a Bernstein's inequality. And just like with Hoeffding, you can get a uniform version of this. And here we're saying for a given hypothesis class, with high probability, for any two classifiers in the hypothesis class, the same inequality holds, except now we've multiplied by a VC dimension, and we've changed the log factors a little bit. OK, and we're going to be expressing algorithms in terms of this. We're going to be using this to design algorithms. Right, so just so I can sort of reduce clutter on the slides, I'm actually going to use a sort of a simplified version of it, which is technically not accurate, but basically I'm shaving off constants and log factors and lower ordered terms just to reduce the clutter. It's sort of a conceptualization of the important parts of the uniform Bernstein inequality, and so this down here is what I'm actually going to be using. But just keep in mind that if you want to make these things formal, you really do have to take into account these the constants and the logs and lower order terms. OK. So with all of that background, let's now dive into the general theory of disagreement-based active learning. So first, I'll just maybe rehash in formal notation what Rob already defined. The region of disagreement of a set of classifiers H. It's just the set of points such that there exist two classifiers in H that disagree on the label of that point. Okay, it's a very simple notion. It's a region of the instance space. And with that definition, we have here a definition of the classic disagreement-based active learning algorithm, the A squared or agnostic active algorithm from Balkin, Bakel, Zimmer, and Langford. So this is a sort of a slimmed down version of the algorithm. So basically what you do on each round, you get some number of unlabeled samples. Let's say on round T, you take 2 to the T unlabeled samples. And we'll go ahead and just here I'll just do it in pictures at the same time. So we'll go ahead and query everything that's in the region of disagreement. Let's say initially everything is in the region. And then we'll minimize the number of mistakes. We'll find some classifier in H that minimizes the number of mistakes on that data. And then we'll actually look at all the other functions in H, let's say this one, and if they make a lot more mistakes than the f hat minimizer, then we actually just remove them from H. We throw them away. So like maybe this other curve that I've drawn makes a lot more mistakes, so I go ahead and throw it away. Maybe this one also, go ahead and throw it away. So what's left is a smaller set. We've sort of pruned the set H down to a smaller set of candidate hypotheses, and the region of disagreement of that set is potentially smaller. And then we iterate. We then draw more unlabeled samples. We just query the ones that are in the region of disagreement. Again, find some f hat minimizer of the number of mistakes there. If there's some other classifiers in H that make a lot more mistakes, we throw them away. So H is getting smaller, and the region of disagreement is getting smaller, hopefully. And we do this for a number of rounds until some stopping criterion. OK, so what's the point of all this? Why are we doing, well, like this step in particular is, sort of looks like Bernstein's inequality. So why are we doing that? So the point of it is that if at the beginning of a round, the best, let's say f star is the best classifier in the hypothesis class, if it's still in the hypothesis class at the beginning, or in the version space, or the pruned down hypothesis class, then because all the classifiers in H at the beginning of a round agree outside of the region of disagreement, if f star is the best classifier overall, then it's still the best classifier conditioned on the region of disagreement. So it still has the smallest risk under the conditional distribution given the region of disagreement. So if we sort of plug that into the reasoning from Bernstein's inequality, what you're getting here is that the empirical risk, the excess empirical risk of f star is bounded by its excess risk under the conditional distribution given the region of disagreement, because that's what Q is sampled from, plus this sort of Bernstein-looking term, this sort of term from Bernstein's inequality. And then, as I just said, f star is still the minimizer under the conditional given the region of disagreement, so that first difference is at most 0. And so what you get to conclude is that f star is never removed. So if f star is in there at the beginning of the round, then given that Bernstein's inequality holds, it's still going to be in there at the end of the round. So this algorithm is sort of preserving this invariant that you never remove the best classifier from the hypothesis class. Right. So it's definitely doing something reasonable in that sense. And then we can ask, well, then how many labels does it use in order to get a guarantee on the excess error rate? And for this, we're going to need to introduce some additional notions of complexity. And this is where this notion of the disagreement coefficient comes in. So I'll define the disagreement coefficient. There's several different parts to it. The first part is this ball of radius r. So this is an L1 ball, essentially. So you take the ball centered at f star of radius r is just the set of classifiers in H such that the probability that they disagree with f star in a random point is at most r. And then the region of disagreement of that ball is just as usual. It's the set of points such that there exist two classifiers in the ball that disagree on the label of that point. So then to define the disagreement coefficient, you take the ball of radius r centered at f star. You calculate the region of disagreement of that ball. You calculate the probability mass in the region of disagreement, divide by r, and take the supremum over r. OK, so that's the definition of the disagreement coefficient. I'll state some guarantees in terms of it, but first maybe let's go through some examples just to make sure everybody follows the definition. So the first example might be thresholds on the real line. This is sort of the simplest example. If you have, let's say, a uniform distribution between 0 and 1, and the set of classifiers are thresholds, so there's some point t such that everything to the right is labeled plus, everything to the left is labeled minus. Okay, so then there's some t star that corresponds to the f star optimal function. And any threshold that is bigger than t star plus r is definitely not in the ball of radius r, because it has distance further than r. And anything less than t star minus r is definitely not contained in the ball. So that's the set. That's the ball. It's the set of classifiers that are have their threshold between t star minus r and t star plus r. Okay, so and then the region of disagreement of that set of classifiers is just that same segment. The probability mass there is 2r divided by r, so the disagreement coefficient is 2. So for thresholds, under this uniform distribution, the disagreement coefficient is just 2. Okay. To go up to a higher dimensional setting, let's consider, let's say, a uniform distribution on the surface of a ball of a sphere in n dimensions, say centered at the origin. And let's talk about the set of linear separators that pass through the origin, so homogeneous linear separators. So f star would be some separator like this, and the separators, other separators in the ball of radius r would be sort of just like f star, except tilted a little bit, just a slightly different angle, where the probability mass in that wedge between the two is at most r. And then if you think about all of the classifiers that are just like f star except tilted a little bit, the region of disagreement that they form is this sort of fixed width slab around f star. And if you actually sort of do the geometry, the width of that slab is going to be proportional to r. And it turns out that the probability mass contained in a region, a slab of of width r is roughly square root of the dimension times r. So if you divide that by r, you find out the disagreement coefficient for this case is roughly the square root of the dimension. Okay, so these are some examples to show that this is a quantity that can be calculated. Indeed, it has been calculated for quite a few different scenarios. And I'll mention a few general things a little bit later. But first, let's get to stating the results. Okay, so I'll start with a simple case, bounded noise. Rob mentioned this, sometimes called Massart noise. So this is an assumption on the type of noise that we're dealing with. And we'll look at two different assumptions in this segment of the talk. So under bounded noise, what we're assuming is that there's some beta, so that it's strictly less than 1/2, such that for every point, the probability that the label is different from f star's label, given that point, it's at most beta. So this is saying that there's some bias toward f star's label at every point. Okay, so this is bounded noise, and the number of samples, the number of labeled samples needed for passive learning, it's known to be about d over epsilon to get the error rate to be at most the error rate of f star plus epsilon. And for active learning, the guarantee here is VC dimension times theta log 1 over epsilon. Okay, so if theta is small, this is actually an exponential improvement in the dependence on epsilon. Another way to view that is it's a rate of convergence in terms of the number of labels. It would be d over n for passive. It would be like e to the minus n over d theta for active. So again, if theta is small, that's an exponential rate. Okay. I'll just very quickly go through some high level of how that proof works. So for any given round, recall that all of the classifiers in H agree on all the points that weren't queried, on all the points that are in outside of the set Q. And so that means that actually in step 4, basically if you were to dump all of the samples that weren't queried back into the data set, it wouldn't change anything in step 4. Okay, so you would still basically be evaluating Bernstein's inequality, but now with all of the data. And so basically the guarantee that that gives you is that after step 4, the only classifiers that are left around have their excess risk bounded by roughly this square root of the distance to f star, d over 2 to the t. And then we're going to use the bounded noise condition. And this condition turns out to imply that the distance between the two classifiers that shows up inside of that square root, it's bounded by a quantity proportional to the excess risk. So you can sort of plug in the excess risk inside of that square root and solve a little quadratic equation. And what you get out is that at the end of each round, the classifiers that survive have an excess risk that's bounded by like d over 2 to the t. And so you know that like roughly log d over epsilon rounds will suffice to give you that epsilon excess risk. Okay. And you can also use this bounded noise condition in combination with that guarantee to say that, to give you a bound on how many queries we made. Well, what it implies is that when you enter the round, h is contained within a ball of radius, like roughly d over 2 to the t minus 1, because that's the guarantee left from the previous round. And so then the number of queries is like roughly the probability in the region of disagreement of that ball, or upper bounded by it anyway, times the number of samples. And then so you just go ahead and evaluate that, and it comes out to, you make roughly theta times d queries on each round. Okay, so if you just sum up over that log d over epsilon rounds, you're going to get roughly theta d log d over epsilon as your total number of queries. Okay, so that was the bounded noise case. We can also look at weaker assumptions. So bounded noise actually makes some assumptions on how the probability of y given x behaves. We can also just look at the general case. We have an arbitrary distribution on x and y. And let's just denote, this is called the agnostic case. So let's just denote by beta the risk of the best classifier in the class. And then we can get this epsilon xx risk guarantee. With passive learning, it turns out you require about d times beta over epsilon squared labeled samples. And with active learning, again with the same algorithm, d times theta beta squared over epsilon squared. So what the difference between these two bounds is we've squared the beta. So we got an improvement in proportional to the error rate of the best classifier in the class, but we also multiplied by theta. Okay, so this is an improvement if theta is small and if the error rate of the best classifier is small. Okay. The proof runs essentially similar, and so I'm just going to maybe skip this for the sake of time. Okay, so as I said, there have been some studies of when is theta small, and we have some understanding of various general conditions in addition to many examples where it's been calculated. So for instance, if we're working with linear separators and the distribution of x has a density and the f star separator passes through the interior of the support of the density. Turns out then theta is bounded, meaning it's not a function of the epsilon. And even if you don't have that second condition, even if you're just in the case where the density function, where the distribution of x has a density with respect to the Lebesgue measure, then at least you can guarantee that theta is little o 1 over epsilon. And it turns out that that's sufficient to guarantee some benefits of the active learning algorithm compared to passive. And then there are some more general conditions that for general function classes, H, there's some work by Friedman from Colt 2009 showing if your hypothesis class is in some sense smoothly parameterized and you have some regularity conditions on the density of the X distribution, and you have some other technical conditions. So the functions are specified as sort of real valued, thresholded real valued functions, and they cross the decision, they cross the threshold at a certain rate and things of this sort. Then the disagreement coefficient is going to be roughly proportional to the number of parameters in that smooth parameterization of the function class. I'll refer you to the original work for all of what the technical conditions are. Yeah, and I'll just mention there are lots more examples and general conditions explored in that monograph from 2014. Okay. A few things remaining that I should talk about. One is I've so far left this stopping criterion in the active learning algorithm sort of vague. It really just depends on what context you're in. You're using this as to what stopping criterion you want to use. You could run this as an anytime algorithm, right? So if you want a classifier Friday at 4 p.m., you can just run it, and whatever the F hat it got on the previous round, it's going to be it's going to have those guarantees in terms of however many label queries it's made up to that time. You could set a label budget if you only can afford a certain number of labels, and it'll just run up until it makes that many queries. And again, you'll get a guarantee on that F hat in terms of what the label budget is. If you have a bounded amount of unlabeled data, of course, you can just run until you run out of unlabeled data, right? So on each round, it's using some number of unlabeled samples. If you run out of unlabeled samples, it doesn't really make sense to sort of cycle through the unlabeled data again or something like that. So that's another way that you can you sort of have to stop if you run out of unlabeled data. Another thing is that this algorithm and this generally disagreement-based active learning algorithms have this property of being self-verifying. And what that means is if you have an epsilon that you're trying to achieve, and so you know what excess error rate you're aiming for, you could just, you could evaluate this Bernstein inequality bound after each round, and it will sort of tell you whether you've gotten there yet or not. You can check whether your guaranteed excess error rate is at most epsilon after each round. So that's another way that you can set a stopping criterion. Okay. I'll mention also there is a simplification of this algorithm that makes a lot of practical sense. And this is based on work from Daniel Su and other co-authors over the years. Basically, it would be nice if you can implement this as a reduction to empirical risk minimization. And that has practical implications because empirical risk minimization can be difficult, can be challenging to run in practice, but you could just maybe plug in a different algorithm there, a different passive learning algorithm, and sort of still get a reasonable behavior in your algorithm. So here's a strategy that does that does this reduction. Basically, sample points now just one at a time. And for each x that you sample, these are unlabeled points from the pool, for each label y, constrain the label to be y, and then minimize the number of mistakes. So in binary classification, you're going to end up with two classifiers, one that definitely labels x as plus and then minimizes the number of mistakes, and another that definitely labels x as minus and minimizes the number of mistakes. And then with those two classifiers, just do this sort of Bernstein check. Is one of them much worse than the other? Basically, if the empirical error rates are very close to each other, then go ahead and request a label for x and add it to the data set. Otherwise, just skip over it, because we can sort of conclude that one of them is definitely worse than the other, so we can kind of infer what f star's label is there. And again, I'm simplifying things a little bit, but not too much. This is a very nice, simple way to do effectively the same thing as these disagreement-based algorithms like A squared. And in fact, this will achieve roughly the same sample complexity as A squared. And the convenience here is that, as I said, this step, this 2, can be, this is an empirical risk minimization step. Okay, so technically there's a constraint there, but you can implement a constraint by just sort of putting in many copies of that example in the data set. And so you can just run empirical risk minimization. Okay, basically what you would do in practice, as I said, empirical risk minimization can be challenging to run. So let's just use a different passive learning algorithm there. And that's kind of one way to make these algorithms practical is express it as this kind of reduction and then plug in a different learning algorithm. And in particular, so in the general case, if you plug in any passive learning algorithm there, maybe you'll lose the theoretical guarantees. But in some cases, you can still maintain some guarantees. So in particular, if you consider a passive learning algorithm that minimizes what we call a surrogate loss, just a relaxation of the 0-1 loss, hinge loss or squared loss, exponential loss. These are some popular losses, right? So now you have some function class that has real valued functions. And then basically you can minimize this surrogate loss function in that step instead of the 0-1 loss. And that's an algorithm that often can be run efficiently. And if you make some additional assumptions, so if you have this bounded noise and then some additional fairly strong assumptions actually on how the hypothesis class and loss function and distribution all sort of work together well, then you can still get this kind of guarantee that you get excess error rate under the 0-1 loss at most epsilon using a number of labels that's still like theta d log 1 over epsilon. And there are various other kinds of results that you can also express. OK. And then I'll just conclude with one other modification, one other variant of this that is definitely worth mentioning. We've been talking about strategies that have like a set, and they'll query if the point is in the set. But you can also talk about strategies that set a probability of querying. And this gets into this importance-weighted active learning idea. So the idea there is on each round, you get this x. And now let's just set a probability, let's say p sub x, that you query that point. And then you flip a coin with that probability as its bias. If it lands heads, you query. If it lands tails, you don't. But if you do query the label, add it to the data set, but add it with a weight 1 over p, or 1 over p sub x. OK. And the reason you do this is because the weighted empirical risk with those weights on the loss ends up being an unbiased estimator of the actual risk. And that's a very general statement. So no matter how you set these p sub x's, you're going to get an unbiased estimator of the empirical risk. You don't want to set them too small if you want to get, because there's some issues with variance and so on. But basically any choice of setting these px probabilities is fine. Maybe just don't make it too small. And that gives you some flexibility to plug in various ideas, various heuristics for designing active learning algorithms. And out of that, you'll get still some kind of a safety guarantee because you're dealing with an unbiased estimator of the risk. And I'll mention it's still possible to recover the disagreement-based active learning just by plugging in a sort of Bernstein indicator function for the px value. So you sort of don't really lose something in terms of theoretical guarantees by expressing things this way, but you do gain a little bit of flexibility. And for that reason, this has been used actually in practical contexts. And right, and of course, at the end, we are running an empirical risk minimization step, but you could use, again, any passive learning algorithm there in practice. There is an approximate implementation of this strategy in the Vopel-Wabbit software library. It's maintained by Langford and cohorts. OK. So that's the conclusion of the second part. We will get into other techniques beyond disagreement-based active learning in the third part. But I'm happy to take any questions right now. And otherwise, we will be taking a short, maybe 5-minute break between. So yeah, if there are any questions, please step up to a microphone. So
the second part, the algorithms had sampling just 1x, but in the first algorithm, you were sampling 2 to the tx, where
yes.
t is the iteration. So can you comment on the practicality of that, and what is the trade-off between the number of samples? And it seems very extreme that one is exponential and the other one is just 1.
Right. OK, so I'll give you 2 answers for this. One, from a theory perspective, the sampling in batches of exponentially increasing size gave us an actually a simplification of the proof. The proof for sampling 1 at a time is a bit messier. Because we were sampling 2 to the t, actually in that proof, we ended up querying about d times theta on each iteration. And that's kind of a nice number because you can add it up a logarithmic number of rounds. And yeah, so there's a lot of simplification in the proof by having this exponential increase in the unlabeled data. From a practical perspective, there may actually be some reason to want larger batch sizes because, of course, you have some team of labelers, and if you give them more at once, they can label pretty fast, actually. If it's 1 at a time, then they're sort of waiting on the algorithm to give them the next query. Yeah, batches make sense in practice in many contexts also. But it is kind of nice to have a simple algorithm that just has 1 at a time also. So there's some, yeah.
OK. Can I ask a question? So my question is there any known minimax lower bound regarding the label complexity of this problem? And if there is any minimax lower bound, so how is the performance of the algorithm that you just introduced compare with the minimax lower bound in terms of the label complexity? Thank you.
Yeah, it's a great question. We're actually going to talk a bit about lower bounds in the next segment. The lower bound, I'll say the lower bound for agnostic learning doesn't have the disagreement coefficient in it. And this is actually an open problem about whether you can generally remove that. And I'll get into a lot more detail about that in the next segment. In the bounded noise case, it's, yeah, it can sometimes be loose, but there's actually a known tight bound for the bounded noise case. Which unfortunately, I won't have time to cover here, but if you're interested, you can feel free to talk to me offline. But yeah, we'll talk about a tight bound for the distribution-free analysis of the bounded noise case. But even in the distribution-dependent case, we know of a tight bound, and we can talk. So
my question is also related to the batch setting. In my experience, batch setting is quite complicated usually because you need some kind of diversity term or something that tells you which batch samples to select, because just taking the n best or whatever based on a certain criterion usually doesn't lead to enough diversity in the samples. Do you have any take on good criteria for batch selection?
Right, so this approach is not actually doing anything with, we don't actually need anything to do with diversity in this approach. So we just have this notion of disagreement. Yeah, it doesn't sort of come up in this context. I think it will come up maybe in Rob's fourth part when we talk about, he's going to mention a little bit about cluster-based active learning, and then definitely there's some diversity that comes into play. But in this context, yeah, that's not really modeled. It might be implicit in there somewhere, but it's not really explicitly modeled. You have a question?
Yeah, so with the same amount of data points, does active learning and passive learning converge in the end, or it's doing better, I guess?
Converge?
Like if I do active learning, but use the same amount of data points as I would do with passive learning, would I give the same classifier?
You're saying the same number of unlabeled data points?
Yes.
I don't think you get the exact same classifier just because of okay, you might be able to prove, with some high probability that it would be the exact same classifier, actually. But that some of that might depend on how you break ties in your empirical risk minimization and things like that. Okay. So what you would have to show is that on each round, you're not just keeping F star, you're also keeping the global empirical risk minimization, the global empirical risk minimizer, which I think you do with high probability. But that would be something that comes out of the analysis, not necessarily a guarantee in